Woo! Hello! Today, in this video, we're going to be deriving the law of cosines, okay? In order to do so, we're going to set up a arbitrary non-right triangle situation here, okay? So we're going to have the triangle set up to where one of its vertices is at the origin and the other vertices are in various spots. So this far spot we'll call it C comma 0, all right? Here we'll denote this as our point B, and so little b will be here. Here we'll denote our point A, which is 0 comma 0 at the origin, and across it will be little a. And here we'll call C, big C, some x comma y, because it's unknown, over here. Okay? Now, this is a arbitrary non-right triangle. So how do we do trigonometry with it when trigonometry is based off of right triangles? Well, out of all non-right triangles, we can create a right triangle. Take a look. If I get this piece, create some altitude, which is a line that is perpendicular, that emanates from that angle to the ground. Notice we get to the x-axis, it intercepts it there. So notice we get two right triangles here. And notice that we can call this height a y, if you will, because all the way from 0 to y, that's the point y, which is corresponds to that point C, which is x comma y. That's why we call it y. No pun intended. So now what we're going to do is derive the law of cosines. So I'm not going to even tell you what it is yet. You're going to see what it is. So notice what happens when we calculate what the cosine of the angle A is. Where it's at this point 0, 0. Notice that that's adjacent. Oh, and I need to specify one more thing. This whole leg is little c, which is the opposite of capital C. And we're going to have to call this section of it x, okay? Just because notice that x corresponds to that x. So it's the amount of horizontal translation to the right, that x, and it's arbitrary. So cosine of A will be that leg length x adjacent over hypotenuse B. So notice that I can solve for x by multiplying both sides by b, and I get b cosine of capital A is equal to x. We're going to remember this guy here. Now notice that I can take the sine of this angle A. Sine of capital A is equal to opposite, which is y, divided by hypotenuse, which is our little b. And notice that we can solve for y. This implies b sine of capital A is equal to our y. Okay? Okay? Now, let's apply the distance formula between these 2 points. Okay? That would be the value A, right? The distance between this point C and this point B is the value of the leg length of the triangle A. Is it not? Clearly it is. And the distance formula between them, if we start from here and we go to here, we have final x minus initial c quantity squared plus final y minus 0 initial squared. Okay? That's the distance formula. x2 minus x1 quantity squared plus y2 minus y1 quantity squared. Square root that and you'll get the distance between two arbitrary points x1, y1 and x2, y2. So we just applied the distance formula here. Notice that this equation gives us that this is the square root of x squared minus 2xc plus c squared plus y squared. Alright? I just FOIL out this term, and we notice that that just gets y squared. Now, we notice that if this is x and this is y, this breaks down to the square root of b squared cosine squared a minus, I'm going to keep this x as an x, 2xc to save board space, plus c squared, and now I'm going to change y squared to plus a b squared sine squared a. Alright? notice that this term and that term shares a b squared. Notice that when we pull it out, we'll get b squared is times the quantity sine squared a plus cosine squared a. Notice that that term will become 1. So I can rewrite all of this as just square root of b squared minus 2xc plus c squared. Alright? And, you know, in order to fill in the steps what I said verbally just a second ago is that b squared cosine squared a plus b squared sine squared a is the same thing as b squared factoring out cosine squared a plus sine squared a. This is equal to 1 by the Pythagorean identity, and so I just get b squared as a result. That's why I could take this term and this term out, rewrite everything, and just put a b squared. That's how we get to here. So, without further ado, I'll give you some time to be able to pause the video and write that down and contemplate it if it didn't make sense. And I'll erase this because I'm going to continue the calculation. Okay, so this right here, notice that this was always equal to a. We go up the chain of equations and over here it equals a. So notice what happens when I square both sides. The radical disappears, and then I'll get a squared is equal to what is inside the radical, b squared plus c squared minus 2xc. Alright, notice that when we replace x with its self over here that we've discovered, this implies one of the laws of cosines. That a squared is equal to b squared plus c squared minus 2c times this, b cosine of a. This is one of the laws of cosines. That is the relationship between the square of this leg is equal to that. Notice that if we didn't have this piece, this minus 2cb cosine of a, then it would be the Pythagorean theorem identically. But this term being there is like a correction to the Pythagorean theorem. Because you don't have a right triangle, you have a non-right triangle. The way you have a Pythagorean theorem for a non-right triangle is this corrective term. This term corrects the fact that you don't have a right triangle. So you can still do Pythagorean theorem on a non-right triangle. And the way you do it is utilizing right triangles. Okay, so that's one of them. That a squared is equal to some stuff. Let's derive the rest of them, all right? And it's not that difficult to do because you follow this same chain of steps here. Another one of them is that b squared is equal to little c squared plus little a squared minus 2 little c little a cosine of capital B. So this is another one, and this is another one. Little c squared is equal to little a squared plus little b squared minus 2ab cosine of capital C. This is another one. And the one that we just derived is a squared is equal to b squared plus little c squared minus 2a little c cosine of capital C. These three are the laws of cosines. These are the laws of cosines. And so we've derived this one right here. I will derive one more and leave the last one as an exercise to the viewers. Typical math textbooks always say things like that. The rest is left as an exercise. And they don't do it because they hate you. And they don't necessarily only do it because they're lazy and they're trying to save printing space. They also want to encourage the reader to be involved in the mathematics, because the only way you can learn mathematics is by doing mathematics. We say that mathematics is not a spectator sport. Matter of fact, mathematics is not a sport at all. It is mathletics. And to get more mathletic, you have to do mathletic stuff. And mathletic stuff involves proving the other law of cosine. So I'll do one more for you here. Let's do this one, this b. So in order to derive that one, I will analyze what the cosine of capital B is. It will be equal to, so this value on this leg, notice, is going to be little c minus x, okay? That's what that leg will be, because the whole thing is distance c. This part is distance x. So this piece will be little c minus x. So the cosine of little b is adjacent little c minus x all over hypotenuse, which is our little a. This implies that that when we solve for x, I multiply both sides by a, I get cosine of b is equal to little c minus x. And so when I add an x and subtract this piece, I get x is equal to little c minus a cosine of capital B. Okay? So we're going to remember this. And then we'll do sine of capital B. That's opposite, which is y, over hypotenuse, which is a. So this one's pretty simple. I get y is equal to a sine of capital B. And this one's pretty simple. Okay? So now, before we were using a, all right, and we tried to find its leg length, little a. Now we're using b. Let's try and find the leg length, little b. What is little b equal to? Little b is given by the distance formula. What is this leg length? So we can start from this a. So final is x minus initial 0 squared, plus final is y minus initial is 0 squared. So I get b is equal to the square root of x squared plus y squared. Okay, so that means that's equal to the square root of this thing squared, little c minus a cosine of capital B squared, plus y. What is our y? This guy. A squared sine squared b. Okay, so now in order to proceed with the calculation, I'll need to clear up some real estate. So we're going to delete this information here and continue the computation up here. Alright, so this will equal square root of little c squared minus 2 little c little a cosine of b plus a squared cosine squared b. I'm just foiling this. This times itself is c squared. Then these is the summation of the middle terms. And this times itself is that guy. Plus what we had, a squared sine squared b. Alright. Notice that these two, when I factor out a squared, I would just get cosine squared b plus sine squared b. And that becomes 1 by Pythagorean identity. So I could just rewrite this, omitting these two terms, and just call that a squared and add it to this stuff. A squared plus little c squared minus 2 little c a cosine of capital B. Alright? Don't forget, this was always equal to little b. We aspired to find what little b is. So remember, I've erased it, but all of this equals little b, right? Little b. So what happens when I square both sides of the equation? That implies I get little b is equal to that stuff minus without the radical on top of it. So it becomes a squared plus little c squared minus 2 little c little a cosine of capital B. Notice this is another one of the laws of cosines. So I challenge you at home, go and prove this middle one. It will involve a very similar argument. Okay? Take the cosine and sine of the angle C, and then take the distance formula, and then solve for that last identity.